Welcome to our seminar on behalf of the Institute for Transportation Studies, on the Citris Banatao Institute, and on behalf of the Berkeley College of Engineering. We are delighted to have you here to our series, Applications of Data Science and Artificial Intelligence to Equity, Race, and Inclusion in Mobility and Transportation. This seminar series is co-organized with Dr. Jane McFarlane, who is the Smart Cities Director of the Institute for Transportation Studies, and myself, Daniel Rodriguez. I'm a professor of City and Regional Planning and Associate Director of the Institute for Transportation Studies. The reason we're here is because of the very rapid growth of data science and artificial intelligence applied to mobility. This rapid growth holds great promise, but also raises some key fundamental questions in many areas: planning, law, social sciences, and public policy, questions that cannot be ignored. So our aim with this series is to reflect on and raise awareness of the applications, of the opportunities, and of the potential misuses and uses of these techniques in mobility and transportation, specifically as they refer to race, equity, and diversity. We want to make sure that we bring a unique and innovative perspective to existing discussions around this topic. So for this seminar series, I am delighted to pass on the mic to my colleague, Professor Trevor Darrell, who will be introducing our guest speaker today. Trevor, please.
Hi, can you hear me?
We can, yes.
Great. Well, it's really my pleasure to introduce Judy. Of course, I know her quite well, as she was my former student, and she is a Berkeley alum and one of the leading figures in research in areas related to diversity and understanding how data science and AI needs to be managed so that we can understand the biases that we have in our data and how we can build deep learning models that either structurally or by various evaluation processes adhere to norms that we expect, and also that work well in new and surprising environments. Judy is now a professor at Georgia Tech, and I'm very much looking forward to her presentation today.
Great, thank you. I'm going to go ahead and share. So hi, everyone. Thank you, Trevor, for that introduction. I'm really excited to be here today. Thanks to the organizers for inviting me. And as was mentioned before, I'm going to be talking a lot about data today. And in particular, I'm going to be talking about how the data that we use to train our AI models can have a pretty profound impact on the performance of these models across many different real-world scenarios. So the focus of today's talk will be on a particular type of AI model, namely those that are built for visual understanding. And given the focus of the seminar, I'm going to have some running examples that have to do with dash cam footage and trying to understand from this sort of dash cam footage semantic concepts that might be relevant for making predictions and actions for these autonomous vehicles. So things like taking an input image and being able to automatically understand what are the relevant semantics of the image. Where are the people in the scene? Where's the road? The other cars? And being able to do this type of understanding is, of course, of great value to any sort of autonomous agent, and especially in driving. And because of its importance and because of the vast amount of research into this space and applications with startups and large companies, there's been a huge focus in trying to leverage some of the advances that we've seen in recent years from the fields of learning and AI and really enact them to aid in this visual understanding process for driving. But the focus of today's talk is to trying to illuminate some of the issues that arise when you take these data-driven approaches. And to understand that, we have to first think about what's the standard pipeline for solving one of these visual recognition tasks. So the first key step in any one of these pipelines is to collect a large amount of data. This data is going to be the information that's given to our models, the information that is used to learn a set of parameters in order to be able to reuse these at some offline time, some deployment time, to solve a given task. And data sets that people collect would look things like this. We have standard visual recognition benchmarks that have been collected to solve various forms of recognition tasks like classification with ImageNet or detection and segmentation with COCO. And more recently, there's been a plethora of different data sets that have been collected, curated, and deployed for the driving-focused application. And I'm showing just a sampling of them here. Now, these driving data sets are usually collected in a similar fashion. You take a car, you fit it together with some sensors, least of which at least you have RGB sensors. Sometimes you'll have a more complex rig that has stereo, LiDAR sensors, and so on. And you'll take these cars and drive them around in natural traffic conditions and collect training samples on the road, interacting with human drivers. And these data sets are very large. Many of them will have hundreds of thousands of hours of drive time available. And they'll look something like this. You'll have a particular route a human driver will take and collect some footage while you drive around. And you'll experience the natural variations that occur in these driving scenarios. Now, once you've collected all of this data, a very critical part of the learning process is then to ask human annotators to specify relevant information that you would like your model to be able to understand from this input data. So in the case of classification, maybe that's that you want to be able to recognize images of dogs. And in the driving scenario, it might be that you'd like to be able to automatically understand, again, where the street signs are, where the sidewalk is, pedestrians, and so on. But being able to collect these sorts of annotations from even just a single frame can be extremely expensive. If you need to have the sort of annotation shown here, which is called semantic segmentation, meaning that you need to be able to understand for every pixel in an image which semantic concept it corresponds to, a single frame can already cost around $10 to annotate. And when you start to think about the amount of vast potential for variation and change in this autonomous driving task, you consider things like weather changes, city changes, or sensor changes, you realize that it wouldn't be sufficient to just label a handful of images. You really need to be able to have examples across all these sources of variation. And so naturally, there's also been an explicit focus on developing driving simulators or leveraging driving simulators that already exist in some cases, and using these pseudo-realistic renderings as a way to generate and easily annotate an excess amount of labeled data. So in either case, whether or not you pay human annotators and take the time to collect these annotations manually or use a pseudo-automated approach, you then have access to this large amount of data together with these annotations, and you can use it to train an AI model. And once we have this AI model, the critical question that we have to ask is, how well does this model perform? And so that's this last step of validating the model. And this is really the focus that I want to place in this talk, is on how exactly are we validating our models? How are we deciding whether or not these models that we trained on a large amount of annotated data are really working, and can we really expect some amount of reliability from them in practice? And so the first and most important question in terms of how are we validating is actually, what are we validating on? So a standard protocol in benchmark visual recognition tasks is to evaluate your model on a held out small amount of data from the same large data set that you used for training the model. This is a really natural thing to do. You've collected a large amount of data. You're just going to randomly sample it into a training portion that you can use for fitting a model and a testing portion that you can use for validating. And when we take this sort of protocol and we train large visual recognition models that can be fit using deep learning, what we find is that these models are able to perform very, very well. And in fact, this last model up here that was introduced in 2017 for this ImageNet benchmark recognition challenge, it was a very high capacity model, fit millions of parameters across this large ImageNet data set, and was able to achieve near perfect performance on a held out test set from the ImageNet benchmark. And so as a result, there's kind of a narrative that emerges that if you have a sufficient amount of data and you can combine it with a sufficiently large, high capacity learning-based model, it's kind of a simple recipe for success. But to test this theory, to understand exactly what are we measuring and whether or not we can anticipate the amount of success from these models, I argue that we have to imagine validating our learning-based approaches outside of the settings that they were precisely trained, and not even necessarily very far outside. But let's imagine taking a model that was trained on this large ImageNet benchmark dataset. It's a dataset developed for classification tasks, and it has the possibility of recognizing across 1,000 different object categories, and it's doing them very well, as we saw in the previous slide. But let's imagine just trying to recognize one of those 1,000 categories, that of a dog, in some related but slightly different data acquisition paradigm. So instead of static images, let's imagine that we're trying to recognize it in a video, this video of a dog running. And it turns out that this large model is not capable of recognizing the dog in the still frames of this video. And to understand why, we have to delve into the data that we've shown to our learning-based solution in the ImageNet benchmark dataset. So this dataset was collected by scraping images from sharing sites like Flickr. And it turns out that people have a very particular bias in terms of the type of data that they like to share with one another. If you're going to share a photo of your pet, like a dog, it's very likely you're going to have the dog's face visible in the image. You're probably going to take care to make sure the dog is in the center of the frame. And you're maybe going to even take a few shots and decide to post the shot that has the nicest resolution, lighting, doesn't suffer from any artifacts. Whereas when you are capturing the action of a dog in a video, you're not necessarily going to take these same sort of curation biases. And as a result, the frames of the video may have different artifacts like lower resolution, motion blur, and a wider variety of poses than you would have seen in that still image database. So this is just one example of a type of bias that might be ingrained into a fixed data set. And we use it to train a model, and it looked like it was performing so perfectly on our held out test set. But if we just tried to take that model and deploy it in a slightly different setting that was maybe captured with a different curation bias, what we find is that the model's performance can degrade significantly. And this is true across a variety of settings. Let's consider the driving example and maybe the particular form of bias that is weather. A lot of these driving data sets are collected around the locations where the companies are located. And many of these companies are in Silicon Valley and going to be driving around the Bay Area or California, where it's just more common for there to be sunny weather. So imagine that you're training this model, this recognition model for these driving scenes, mostly on sunny data. And then you would need to ask yourself, well, how well does this model perform when it's no longer sunny? Maybe when it has a substantial amount of snow on the ground. And so if we were to take an off-the-shelf model that was trained mostly in sunny weather conditions and try to use it to predict where the road is, where the buildings are, and so on in this scene, we'd end up getting a predictive output that looks something like this, where there's a lot of misclassification, there's a lot of mistakes. In particular, even the road, which is normally not one of the most challenging things to recognize in one of these images. But even the road is here being misclassified as a building. And so to understand how we might attempt to mitigate some of these biases, my work, as well as the work of my colleagues, have focused on this idea of domain adaptation. And what we do with domain adaptation is we assume that we have access to some source of large and annotated collection of data. It might be that curated database called ImageNet. It could be a collection of images that we'd like to recognize of objects as they appear in a product warehouse. Or it could be those driving images that were generated in simulation. But in any case, the goal here is to be able to find a way to leverage the information that you can learn automatically from the large annotated data sources without overfitting or over specializing to the particular biases that exist in that original data. So to make sure that you're able to still recognize in that video domain, or can still recognize when you see these products that you'd like to recognize, but as they appear naturally in an office environment. Or to take these models that you've learned mainly in simulation and make sure that they still are able to correctly understand the real visual world. And so for this, we take an approach called adaptation, which is really just a technique to leverage some of the statistics of the large annotation dataset, as well as the sparsely or unlabeled test time dataset, and learn to find information that can be reused across the two scenarios. I'll give you one example here. This is a style of approach that has been used across a variety of different research papers in the last few years. And this style of approach is called domain adversarial learning. And what it does is it first imagines training a classifier to be able to recognize the objects of interest, or more broadly, training any sort of visual recognition system on your large annotated data set. Of course, the problem arises when that model no longer has strong predictive performance as the environmental conditions of capture, curation, or just in general bias of the target dataset changes. And so the idea of how to mitigate this is to introduce an auxiliary learning objective, which explicitly asks for that large annotated dataset to focus on learning to extract information that is reusable across the two different data conditions. And the way that we do that is by first learning what's called a domain classifier. The job of this model is to be able to predict whether or not an intermediate latent feature vector arises from your source data or your target data. And then to update the model with an adversarial loss, which attempts to confuse that domain classifier. Intuitively, what's happening here is that you're seeking to impose an invariance constraint on the learning process by making sure that once you've extracted information from the two different sources of data, on average, that information is indistinguishable. So you're not extracting specialist information or information that maybe overfits to the idiosyncrasies of that labeled data set and doesn't generalize to the new domain. And this can be deployed at intermediate features or directly at image features. And we use both style of approaches in our work. So once we've used one of these techniques, what we can do is we can study these adaptation problems across a variety of different scenarios. The first one that I mentioned earlier is imagine you're training mainly in fall weather conditions, and then you want to evaluate how well your model can perform under snow conditions, or more broadly, winter conditions. So the first thing that we'll do is we'll perform pixel space adaptation, which is going to take in one of your large labeled data set images. In this case, it'll be a fall image, and it's going to attempt to re-render this image so that its appearance more closely mimics that of the deployment scenario, in this case, winter. So we'll start with this image, and once we have performed adaptation, we'll be able to produce this output image. The main changes here are just that snow has been deposited on the sidewalks and on the roofs of buildings. So now if we want to try and adapt our original fall model and deploy it in this winter condition and study the performance on this particular image that has snow in the scene, the desired ground truth output would be able to recognize things like the road, shown in purple here in the upper right-hand corner. But before we did any adaptation, when we just leveraged that model that was learned on fall images, we confused the road with buildings. Whereas after adaptation, we're able to start to successfully recognize it as the road that it is. So this is a promising direction. And as I mentioned, there's been a large body of work into these styles of approaches. But overall, this type of approach is really focusing on aggregate statistical measures and trying to understand the overall appearance of these images in the two conditions and attempting to do distributional alignment across these two settings using these marginal statistics. And unfortunately, when we're in a situation where the type of data that we're collecting and the types of objects or attributes that we would like to recognize is imbalanced, this style of approach is likely to fail, or at least likely to overvalue the categories, the information that's most prevalent in the data. So more recently, we studied this problem of being able to adapt even in the scenario when at test time, your data might be imbalanced. Now, for your source data set, the one that has access to labels, you can always artificially balance the data, meaning that even if you have extra samples of pedestrians and fewer samples of road signs, you can always, using the labels that are available to you, resample in order to produce a balanced set. But naturally, some objects are more common than others out in the world. And so when we're talking about deployment time, we may not have this capability. And especially if we don't have access to labels overall, we may not be able to do this type of explicit resampling. And so as a result, the distributions between our original training data and our deployment data are not only going to have different appearances, but they might even have a difference in terms of the distribution of the objects and the information, the type of labels that we want to be able to predict. And so the goal of this work was to be able to both adapt under changing data distribution, but also under changing label distribution. And a really common style of approach to address this type of problem is called self-training, where either by using pseudo labels, meaning the current model's best predictions, or by using some alternative like entropy minimization, recent approaches have been able to achieve state-of-the-art performance on this type of task using a combination of these self-training approaches. And critically, these style approaches seem really appealing because they don't make any assumptions about there being a shared label distribution between your original avenue of training and the way that the data appears at test time. But there's some pretty distinct downsides and limitations to self-training style of approaches. I'm going to show you one example here. So imagine that we have our original labeled source data set. It has two categories, circles and triangles. And because we have labels, we can learn some type of model that's able to separate our our feature space and predict whether or not a new data point is a circle or a triangle here. Now, when we are confronted with domain shift, meaning that we have data that was collected under a different set of biases than our original labeled data, it may result in our new unlabeled data points falling at some point in our feature space such that they're not well separated under our source model. So we see that here because there are some triangles that end up on the circle side and some circles that end up on the triangle side. And when you're in this sort of situation of poor initialization, what happens is if you take a self-training approach and you want to use a technique like entropy minimization, which basically just means that you would like to increase the confidence of the model for the current predictions. So if you're currently predicting that an example is a circle, you want to figure out how to update the model so that you become more confident in this circle prediction. But if that prediction is wrong, then you have this situation of reinforcing errors of the current model. And that may lead to a further misalignment than what you even started with. And so in our recent work called Sentry, what we try to do is we try to leverage some of the benefits of self-training approaches, which can be deployed in a more flexible set of circumstances for adaptation, but don't necessarily suffer from the same degradation in performance or degenerate solutions that exist in unconstrained self-training approaches. So here's the idea of what happens. The key idea is that rather than optimizing our data for a standard self-training objective, we're going to impose an adaptation criteria only on samples that we deem to be reliable. And we're going to judge reliability using a form of predictive consistency. Now, overall, other approaches have attempted to use additional measures of reliability, such as just the model's innate confidence. But in these kind of domain adaptation scenarios where the data does not match the training time assumptions, what happens is that there's an issue of calibration. And so the scores of a model trained in one setting, so maybe trained in fall and then deployed on winter, it's not just that you're misclassifying the road as a building, you may not even have a reliable confidence measure on that prediction because just too much about the input data has changed. So we want to be able to find points that we think will be reliable and explain next how we do that. And once we find those points, we can then use self-training objectives to be able to optimize the confidence of those points and result in an alignment that improves our overall visual understanding performance on this new deployment setting. So this method Sentry, the way that it works is that we first imagine training a supervised learning model using our input labeled data. And here I'm depicting our source data as being this sort of sketch of a bear. Whereas maybe at test time, we want to be able to recognize how the bears actually appear as you take a photo out in the wild. So first off, what we might consider doing is just taking the model out of the box that we trained on this kind of synthetic data and just evaluating it on our real data. We'd like to be able to improve the model rather than just taking this original output. We'd like to adapt it to some of the differences between this sketch setting and this real world setting. And to do that, the way that we're going to judge reliability of the model for this particular visual input is we're going to impose a set of label preserving transformations on the image, pass all of them through the model, which will each produce a set of predictive outputs. And then we're going to optimize over a selective self-training loss. Now, this selective self-training loss is going to first and foremost judge whether or not these predictions from all of these different deviations of the same original image are consistent. And this can be using simple techniques like majority or unanimous vote. And if the model is consistent, we're going to attempt to update our learning objective so as to increase the confidence of this sample. And if we found that the predictive outputs are inconsistent, then we're going to attempt to decrease the confidence on this sample. So it's a pretty simple change from what we had before. The key difference is that rather than always trying to optimize or increase the confidence on the current predictive outputs, we're instead going to make sure that we judge a sense of reliability for each instance before we focus on increasing confidence. And in fact, if we find that an instance may even be unreliable, we're going to attempt to move that point closer to the decision boundary by lowering its confidence overall. I'm going to show you some results of this work first on a couple standard benchmark data sets for domain adaptation in the visual recognition community. And then I'm going to show you an example of some preliminary work applying these to driving images. So first off, there's a data set called Mini Domain Net. And this data set has access to 45 different categories, as well as 6 different domains. The domains are shown here. We have things like clip art and sketches, as well as real images. And the idea is you want to understand how the bias of these original sources of data, if you were to train on them, how well could you effectively adapt that model for use in a new test time setting. And the natural distribution of these data sets, when they have not been explicitly curated, is already unequal. So on the left-hand side, we have the distribution of each of these categories in terms of the count of the number of instances, both between clip art and sketch, and there's a similar phenomenon that's found between the other domains as well. So we really do need to be able to adapt not only between the appearance changes here, but also between the variance in terms of the number of objects instances per category. And overall, we can imagine computing the accuracy of our model, where what we'll do is we'll set up the learning problem as having pairwise shifts, training on one domain, testing on another, and doing it in a round-robin fashion across them all, and averaging the results here. So a standard model that did not do any adaptation would be able to achieve about 66% accuracy on this task. Prior approaches that focus on distribution matching-based techniques, these are the techniques that I was mentioning earlier, like domain adversarial learning, where you are really making an implicit assumption that there's some sort of consistent label distribution between the two settings. These techniques tend to either improve subtly over the source, or even some cases performing just about the same as doing no adaptation. Using a technique that's based solely on label shift doesn't account for the fact that there's appearance shift here and underperforms the original model. Accounting for both improves performance a bit more. And ours is able to achieve a performance above the leading state of the art at the time of the creation of this paper. And this idea of studying label shift doesn't have to just be in a subtle way where one category maybe has a few more instances than another. You can also imagine creating an adversarial scenario where the training data, the most prevalent classes there are precisely the least prevalent classes in the test data. And this would be used just to stress test our algorithms to understand how much they might degrade when this assumption of a similar label distribution is really, really violated. So this data set called the Office Home, very similar to the Mini Domain Net data set. It has a sequence of different domains as well as categories that you need to recognize. And we're going to operate on this kind of adversarial setting where we have common classes in the real world are precisely the uncommon classes in clip art. And again, we'll do this in a round robin fashion, and we find a similar trend where our method Sentry is able to outperform prior approaches, even those that consider the label shift explicitly. And if you're interested in this work, we have a paper on arXiv, and we were able to achieve state-of-the-art performance in 27 out of 31 shifts of that we studied. Now, given that this audience is interested in transportation, you may be wondering, how can we employ some of these techniques on the self-driving images? And it turns out that you can do similar things, so I don't have time to go into all the details that are different. But in brief, when you have access to these large driving images and you want to be able to perform adaptation using some form of selective entropy, you can consider alternative forms of measuring reliability. In fact, you now are starting to have predictions across multiple portions within the image rather than a single prediction for the image itself. And so instead of only using artificial augmentations, you can also combine those together with looking at predictions and accumulating predictions across the image in various different spatial regions. And so we use an approach like this in order to study the problem of adaptation from the GTA dataset, which is a collection of synthetic images taken from the Grand Theft Auto game. They're decently realistic, though definitely not all the way there. And we evaluate our model on the Cityscapes German driving dataset. An example of that is shown on the right. And once we do that, we're able to achieve improved predictive performance by using a variant of this selective entropy. We start with an image that we'd like to be able to recognize, shown in the upper left. The desired output, ground truth, is shown in the upper right, able to accurately recognize all the pedestrians right in front of us and the signs in the background. And when we just train in simulation and evaluate directly on these real images, we're already getting some kind of a reasonable performance, but there's still a lot of errors arising. And that's shown in the bottom left. And in the bottom right, we have what the output of the system would be after performing some amount of adaptation. I want to alert your attention to some of these regions where you can see that some of the local mistakes that are being made by that original synthetically trained model are being partially mitigated using this approach, as well as this region over here with the sidewalk, which was originally confused with terrain. So until now, I've talked about performance degradation and showed you a number of different examples of how bias in your original data set can lead to lower performance in a different test set. And many times the difference that arises in the test set are very natural, like training on a curated database of cropped images and then just expecting that it should be able to perform well on frames within a video. Or training on a collection of outdoor driving scenes and expecting that they should be able to generalize across a variety of weather conditions. Or finally, trying to leverage the data that you can easily and cheaply acquire from simulation and adapt it for use in real-world imagery. In the remaining part of the talk, I want to address how these sort of biases, which appear benign in the examples that are shown on screen now, may actually lead to systemic inequity across different demographics. And this can be a result of finding that systems explicitly underperform on certain subpopulations, or it can also be a result of having data that just has a substantial underrepresentation of certain populations. In the study done in 2019, looking at geographic bias of common visual recognition data sets showed that the majority of the images that we're using to train most of our benchmark models and to develop new models on does not accurately represent the world population, and in fact has a very significant bias towards images arising from North America and Western Europe. And what this means in practice is that our definitions that we train our models to learn may not match the same definitions around the world. So take this example. What does spices mean? What does spices look like in the US and maybe in Western Europe versus what do they look like in the Philippines? And if you're only teaching your model that spices look like the example on the right, we'll have no hope of deploying a system that can recognize the same concept as they appear in other parts of the world. And in fact, that's what this study looked at, was they said that we had models that are trained on the data from these big data sets and others. And if you were to evaluate the performance of those models on images that are collected from around the world, you'll notice that you have high performance, close to 90% accuracy in the regions that had high representation, and substantially lower performance elsewhere. Now, the same geographic bias actually exists in our driving data sets as well. So if we were to look at two different driving data sets, this cityscapes on the left is mostly a collection of images around Germany. And Argo is a dense collection of images around two US cities, Miami and Pittsburgh. And so the fact that we have these very distinctive geographic biases will definitely make its way into the systems that we learn. And if we are still using these same biases in order to evaluate our systems, there may be deficiencies that are not even illuminated because we don't have access to the data in order to evaluate them properly. And the geographic bias doesn't have to stem at a world scale. It can even be within a city. So here's one snapshot of the regions within one of the German cities of that cityscapes dataset where the drives took place. It's not a dense drive across the whole city. And in fact, more than just the fact that the data does not span across every part of the city, it also, the model itself is usually evaluated as an aggregate across an entire collection of data, rather than looking at the performance of the model as it may either overperform or degrade across different regions within the city. And so we did a preliminary study just to evaluate the performance of a model that was trained on this data set and performed well overall, but found that there are certain regions where it performs substantially worse than others. And so if these regions happen to align with certain demographic groups, that would be extremely undesirable, and it would be something that we really need to make sure to investigate and mitigate. Now, sometimes the performance change in terms of different parts of the city could be due to things that sort of make sense, like the fact that it might be more challenging to recognize different parts of the road in city centers where there's a lot of occlusion and pedestrians walking and cars that are parked on the side of the road or driving in the middle, versus this highway where you can make a lot of very distinct implicit assumptions about where you would expect certain objects to be. But overall, the key idea here is that we saw in the standard recognition paradigms that it was so critical to make sure that we evaluated our models on the types of data that we may encounter at deployment time in order to both understand the way that we expect them to perform overall, as well as to attempt to mitigate any deficiencies in our current systems. And these sort of issues in terms of bias in the data set may be due to an underlying geographic bias, but it can also be due to a curation bias or a data collection bias problem. There was this unfortunate incident a few years ago where a big popular recognition model was deployed and available for public consumption. And it was found that when that model was deployed, all of a sudden it was being used on a collection of images that didn't necessarily somehow make its way into the initial evaluation. And in fact, a really egregious error was made by the system to misclassify darker skinned individuals. So to study this kind of problem, there was a seminal work introduced in 2018 called Gender Shades, which set out to study the disparity in commercial gender classification platforms. And first and foremost, one of the key takeaways of this work was to just point out that if you were to study the distribution of darker versus lighter skinned individuals and also male versus female individuals in these data sets that are used to train models to recognize gender, you'll find that there's a very distinctive bias here. And in particular, if we look at this second data set, only 4.4% of the data set even has examples of darker skinned females. So in this study, they realized that, well, before we can even go about understanding what is the bias and how much predictive inequity there is in these systems against both, in this case, gender and skin tone, we have to collect a different data set that allows us even to adequately study this problem. And so they collected this data set called Pilot Parliaments Benchmark, where they tried to normalize for the size of the faces by making sure that they were getting headshots, and they got them from public figures so that there was kind of a standard protocol for how these were acquired, and they were decently high resolution. But they were collected from different parts of the world, and in particular, they took care to make sure that this data set had adequate representation across both gender and skin tone. And once they had that data set, they were able to evaluate off-the-shelf systems for gender recognition and found that these systems, while they had perfect performance on lighter skinned males, had quite poor performance, even up to above 30% error on the lighter skinned females, or sorry, the darker skinned females. So this really illuminated a problem in both our data sets, but also in our evaluation pipeline against demographics. Now, if we go back to our driving example, we think about the way in which these data sets are collected. They're just driving around certain portions of certain cities, maybe sometimes a day. It may also be true that these data sets have a similar sort of bias against different subpopulations. And it's just as a result of where these cars drove and who happened to be there. And so to study this, we deployed a similar protocol as was used in the gender stage work, namely to use the Fitzpatrick skin type labeling, which is a designation that was developed by dermatologists based off of how likely the skin is to burn. An example of the colorations are shown in the upper left. And we set up a mechanical Turk problem where we asked users to label for each crop of a person in the data set whether or not this person was from either a lighter skin or darker skin category. This is kind of an example of a task that might be shown to an annotator. Now, sometimes it would be impossible to tell. Maybe you'd know there was a person, but for whatever reason, they're cold outside, all of their skin is covered up. You can't really tell about the skin type. So for the purpose of this study, we would ignore those types of samples. But we end up having outputs that look something like this, where together with the ground truth person annotation, we now have an auxiliary annotation that identifies the person as either lighter skinned or darker skinned. And again, we do this as a way to start to measure the performance across these different subpopulations. Now, overall, we asked for these types of annotations from 3 different annotators and made sure that we had a consensus vote before considering one in a category or another. And what we found was that there was a similar kind of bias that existed in those object detection and gender recognition data sets, namely that there was substantially more lighter skinned than darker skinned individuals. And unfortunately, this performance or this data collection difference translated into a performance difference where there was also higher performance at recognizing the pedestrians with lighter skin than those with darker skin. So a natural question would be to ask, what causes this performance drop? Well, the most natural answer would be to look into whether or not it's caused by the lack of training data. But unfortunately, to answer that question, you have to go out and now collect more driving scenarios. You have to then annotate those with all of the people and all of the other categories that you'd like to recognize in the image. And then you further have to annotate with lighter and darker skinned individuals. And you probably had to take care in terms of where you drove to make sure that you drove through neighborhoods that had a particular distribution of people that mimicked the type of data that you were missing. And even that is likely to be a really biased way to go about it. Algorithmically, we tried to understand whether or not different amounts of training data could impact the output performance by using classic techniques like reweighting or rebalancing. It didn't seem to improve performance in this case. We also attempted to understand whether or not there were confounding factors that might have caused this drop in predictive performance by looking at things like whether or not this predictive performance persisted across different times of day or across different measures of occlusion. And again, found that this performance drop was consistent even among these controlled factors. So overall, this is a really challenging problem. And I've talked about both how bias in our original training data can lead to degraded performance, even when that bias exists on things like our dogs that we took photos of their faces, or exists because we happened to collect images mostly when it was sunny outside. But a key takeaway from trying to understand these challenges and address all of these forms of bias is first and foremost that measuring each form of bias, or even before that, defining the types of bias that could potentially exist, is both time-consuming, costly, and also susceptible to its own form of errors. Of course, if we attempt to mitigate these issues, it becomes really important to try to disambiguate whether or not there's a systemic issue with the model that we are creating, the technical solutions that we are deriving, or if it's all a result of the data that is being used in order to supervise the learning of these models. And unfortunately, currently, for studying at least demographic bias, there are some populations that are so poorly represented, there's not even sufficient data today to really statistically significantly make claims about the performance of these models. Like, we have so few that we have to even just collect more to be able to adequately measure. And there's some technical challenges that arise in some of these later examples. Namely, if we have so few examples, leveraging some of the technical domain adaptation learning-based methods that I showed you earlier in the talk may not work very well, because those techniques really rely on having enough samples, maybe without human supervision, but enough samples overall to be able to start to understand and extract patterns from the data. So in summary, we have this very standard learning-based pipeline for solving a task like visual understanding or visual recognition. But it's really critical that when we are trying to evaluate the performance of these learning-based systems, we both understand the data that we're using for training, but also for validation. And it might be important that we not only validate our model on data that is similar to that which we use for training, but also on data that is slightly outside of the scope. It may help us to understand the failures and the biases within our systems and hopefully mitigate them before we deploy them in practice. I want to take a moment to thank all the members from my group, as well as those that were shown on the slide for the specific work. And now I think we'll have maybe a couple of minutes for questions. Thank you.
Judy, thank you very much. That was very, very stimulating and a tour de force. It's wonderful. Thank you again. You're right. We are tight on time. And I want to invoke the privileges of the moderator and ask you a question. Not being a person that works in this space per se, it strikes me that the key here is to attempt to know or suspect what you don't know. And so I'm wondering whether you have advice for young researchers, for folks that are getting into this field, on how to approach precisely those biases, those what they don't know that could affect either the model performance or the data quality, and that ultimately will degrade the whole project.
Right, that's a great question. And in general, it's exactly what I was bringing up at the end, which is that this is very, very challenging. And in fact, if you are even if you think of a particular source of bias, it may be prohibitively expensive to collect the supervised annotations to really measure it properly. And so this is an area where collaboration between the communities that are studying these tasks together with the communities that are working on the more technical model development is really, really important, because there are many different communities that are working in ethical AI and algorithmic fairness today. There are whole conferences and journals devoted to these tasks. And quite frequently, those researchers may not have access to the late-breaking models and different innovations that exist across the more machine learning oriented or more broadly transportation oriented communities. And I'll give you one example of this. I know that there are communities that are working today on things like data visualization, or trying to understand how to break down your data set into different subcomponents and analyze in hopefully some automated or at least in some interactive fashion what is the different predictive performance across different subparts of the data. And those are people who are experts in understanding data and understanding how to communicate things about the bias in data. If they get to work with people with the data sets that we use in our literature and work with you to understand something about your model specifically, they may be able to in turn update those visualizations to integrate some of the specifics of our late breaking state of the art work.
Great, Judy, thank you. Let me open the floor, or I guess the Q&A. If anyone has a question, to please go ahead and share it. We probably only have time for one of them, but if you have one, please go ahead and submit it. Well, Judy, it looks like nobody's right now typing something. I want to make sure that we don't go substantially over time. Again, I want to thank you very much for the presentation. We really enjoyed it. And we look forward to seeing your trajectory. I was amazed at the number of accolades you've collected. You've been awarded the NVIDIA Female Leader in Computer Vision Award last year, AI Minor Top 100 Most Influential Scholars in Machine Learning, and an MIT EECS Rising Star in 2015. So congratulations for all that work. And for us, it's a privilege to have you here sharing all your knowledge and your perspective. Really great to have you. Let me now turn to the farewell. We have one last seminar coming up. Bernie, if you could please put that slide up. Thank you so much. This is our sixth seminar for this speaker series from Siemens Mobility ITS. We have Larissa Parker, who is Vice President of their ITS Digital Lab. We look forward to that presentation, and please make sure to join us at that time. Look out for the announcements and for the registration. It's going to be a week from today at the same time. So to all of you, and especially to Dr. Hoffman, thank you so much for being here. It's a pleasure to see you all, and thanks for sharing your insights about the topic. Till next time.